One challenge that we have with convergence of sequences is that there isn't a general set of rules or procedures that we can use to determine whether or not an arbitrary sequence converges. So when mathematicians find themselves in this spot, they do what you've already seen with integration, which has a similar kind of limitation. We look at subgroups of the problem that have specific properties and that hopefully occur a lot in practice, and we see if we can answer the question definitively for that subgroup. So in this lecture, we're going to apply that approach to sequences. So I've got several definitions here that are going to lead us to a subgroup, a type of sequence, where we'll be able to make some concrete statements about whether or not they converge. Now, you can read through these, and they're pretty self-explanatory. The math definitions pretty much match what we mean in English by increasing, non-decreasing, etc. The key difference you should focus on is whether or not the inequality is strict, like in the definitions of increasing and decreasing, or if it includes the possibility of equality, like in the definitions of non-decreasing and non-increasing. In those cases, the sequences are allowed to, in some sense, level off or stay constant, as long as they don't just completely change direction and start going back in the opposite way. So, referring back to my previous comments, right, about interesting subgroups, the group that we're going to be focusing on in the next several lectures, and that we can make some general statements about, are so-called monotonic sequences, right? That's a category that includes both the strictly increasing and strictly decreasing sequences. So I've got a few more definitions here, which you can read over. They all talk about different types of limits that we can put on the values of a sequence, both above and below. So on the next couple of slides, we'll look at some examples of these, and I think that'll help to clarify some of the more technical terminology here. But ultimately, bounded from above just means that there's a ceiling. There's an upper limit past which the sequence never goes. A lower bound means there's a floor, right? A lower number beyond which the sequence never goes. Sequences that have these properties are called bounded from above or bounded from below. Typical math, right? Not the most creative naming conventions in the world. And a sequence that is bounded from above and below, we describe with this more general term, bounded. A sequence that doesn't have that property, that either is unbounded on both sides or that is only bounded on one side, is what we're going to call an unbounded sequence. Okay, so let's look at some examples here. The graph here graphs the first, 15 points of the sequence A sub n. And you can see a couple things from this. First, this sequence is decreasing. Right? It never turns around. Not only does it never turn around, it never levels off. Right? So it is a strictly decreasing sequence. And it is bounded. Right? It's bounded above by 0.5. 0.5 would actually be the least upper bound. And it's bounded below. This is, you can't quite see this from the graph, although you could infer this by taking the limit of there as n goes to infinity. It's bounded below by 0, and 0 is also the greatest lower bound. Now, just so we're clear, there are other bounds. Right? I could say that this sequence is bounded above by 1, for example. In fact, it's bounded above by every number greater than that least upper bound. Right? But it's usually the least upper bound and the greatest lower bound that are going to be the most interesting numbers. All right, so suppose we take a look at the sequence B sub n here. I've got a graph here for us to look at. This one is also monotonic. I don't know if I said that about the first one. The first one, in addition to being strictly decreasing, is also monotonic. This one is both monotonic and strictly increasing. And again, it's bounded as well. It's bounded below by 0.5 is maybe a little hard to see there. But B sub 1 is 1 minus 1/2, which is 0.5. And it's also bounded above by 1. So this is also a bounded sequence. All right, so how about... So I've got a graph of the first 15 or so terms of C sub n here. And hopefully you can see from this pretty quickly this is not monotonic. It's got this sometimes going up, sometimes going down behavior. So it's neither increasing nor decreasing, and it's also not non-increasing or non-decreasing. right? The bouncing up and down behavior eliminates all of those options. It is, however, bounded. It's bounded above by 1. That would be its least upper bound. And is bounded below by -1. That would be its greatest lower bound. Or then this last one here, d sub n, this is none of the above. It's got that bouncy behavior, so it's not monotonic. It's not increasing or decreasing. And it's also unbounded in both directions. Right? It's not bounded above and it's not bounded below. So you've seen some examples here of kind of a bunch of different combinations of those properties. So in the next lecture, we're going to look at an example of kind of an interesting sequence. So we're going to see how to determine whether or not it's monotonic. Then in the lecture, that's going to be just an example lecture. In the next full lecture, we're going to look at something called the monotonic sequence theorem, right? And we're going to see how for sequences that are both monotonic and bounded, we can come up with a definitive answer about whether or not the sequences converge or don't. So the links to that are here on this page. And of course, if you like this lecture, please don't forget to click on the like button down below as well.